Perfect. Thank you. All right. Hi, everyone. This is Apoorva. Really excited to be here today. I was listening to Ria and Paula's talks, a really solid set of talks to follow. So I hope that I can keep the momentum going. But today, I'll be talking to you about how to achieve artificial general intelligence. I'm joking. That's too much to unpack in 30 minutes. And I definitely don't have all the answers, but I'll be discussing something that's equally fundamental, which is how to build memory management systems for AI agents so they can truly learn from their own experience and collaborate intelligently with us in the future, because that seems to be where the AI space is going. And I think it's going to impact the future of humanity in a pretty significant way. Right, so here's a bit about me. Last year, I moved into my first developer advocacy role here at MongoDB. So, as a dev advocate, I create technical content, hands-on workshops, and talk to developers like you to inspire them and help them build AI applications using MongoDB. And prior to that, I spent about 6 years working as a data scientist in the cybersecurity space. And outside of work, I read a lot. I'm currently learning how to sketch urbanscapes, and I'm always on a mission to try as many local coffee shops in whichever city I'm in. So I see people tuning in from all over the world. I hope to be at a coffee shop near you someday. All right, in my short talk today, I'll start off by briefly talking about what AI agents are in the generative AI era, set the stage for why this conversation about memory is important. And I'll then talk about the different types of human memory and how they map to agentic memory, since agents are software systems. And also spend some time talking about what it means to CRUD, or create, retrieve, update, and delete memories in AI agents. And finally, I'll wrap up with what I'd like your key takeaways to be from this talk. And hopefully, we'll have time for some Q&A as well. All right, so let's jump right in. Very quickly, let's talk about a little bit about what AI agents are for those of you who might be new to the concept. So AI agents have been around for a long time, at least since the 90s. So reinforcement learning agents were the original idea of AI agents, where a machine learning model selects from a set of actions to maximize rewards based on environmental feedback. And this reward feedback loop is what helped these agents master games like backgammon, chess, Go, and even beat the grandmasters of their time. But with the advent of LLMs, the term AI agents has been has increasingly referred to LLM-based systems. So in this talk, whenever I say AI agent, I'm referring to LLM-based agents rather than reinforcement learning-based agents. All right, so AI agents, whether they are RL-based or LLM-based, have pretty much the same components. So there's perception, which is what allows them to observe and interpret their environment. Action, which is how they interact with their environment. Memory, and this is how they maintain information about past experiences, state, and knowledge. And feedback, which is signals from the environment or user that help guide the agent's future behavior. And with LLM-based agents, we also have an additional component called reasoning, which means they are able to reason through a problem on their own and determine the course of action to solve the problem. So in the context of LLM-based agents, perception typically comes from inputs to the agent. And this can be human-generated, where you are interacting with the agent, or triggered by some sort of system, for example, Slack or an email. And these agents take actions with the help of tools, which can be anything that you can convert into an API. They can be specialized machine learning models, vector databases. Yeah, basically anything that has an API around it. Then the agent's memory comes from its past actions or interactions with the user or their environment, the environment that they're running in. And feedback comes from the tools it executes, users, and the environment. And finally, LLMs are the brain of the agent that help it reason and make decisions. So then the definition of an AI agent in the generative AI era becomes this, or this is how I like to define it anyway. An AI agent is a system that uses an LLM to reason through a problem, create a plan to solve the problem, execute the plan using a set of external tools, and iterate on the plan using feedback from tools and past interactions. And this is huge. With agents, we have augmented the world knowledge of LLMs, which are already pretty powerful models, with and we've augmented their reasoning and natural language understanding capabilities further with the ability to take actions. Which is why, with agents, a future of full autonomy, which is the eventual goal of artificial general intelligence or AGI, even seems possible, right? And freakishly closer than it has ever been before. But trust and reliability are a big part of us being able to look at these agents as partners in doing things as we move forward with these models. And the good news is that things are improving constantly and rapidly. Where we could interact with LLMs using only natural language and text just a few years ago, we are already at a point where we are able to interact with them using other modalities such as image, voice, or a mixture of all of these. LLMs are also getting better at reasoning. So where we used to go back and forth with these models to reach an outcome, we now have large reasoning models where we can simply give these models a problem to solve and have them plan, reason, reflect, and even refine their path to reach a final answer instead of hand-holding them through the problem solving. But there's one aspect of agents that you don't hear too many people talk about, at least not yet. I am seeing conversations in the community, but I don't see as many people as I'd like talking about this yet. And this is something that's truly important for agents to augment our agency in the future, something that will allow us to truly feel comfortable putting them in charge of some of the steering of the metaphoric vehicle that is our own lives. And that's memory. Like I said, to be fair, most LLM applications today, we do see some form of memory, and it manifests as chat history, which gives LLMs context of past interactions in a conversation to maintain coherent dialogue. And this works in most cases for now, since the scope of what we are using LLMs for is very constrained or limited. But as we expect LLMs and agents to execute more sophisticated tasks, we are going to want them to be more intelligent than they are now. Imagine if we only remembered our recent conversations and nothing beyond that, we wouldn't be, quote unquote, the most intelligent beings like we think we are. But we don't work that way, right? At a high level, humans have two types of memory. We have short-term memory and long-term memory. So let's talk a bit about these and then see how or if these translate to software systems like AI agents. So short-term memory basically helps us remember not just conversations from the recent past, but also observations such as the weather you looked up a minute ago. And there's even a shorter term memory called working memory, which temporarily stores information that is being worked on actively. For example, if you're solving a math problem, any intermediate calculations you make while solving it is what is stored in your working memory. But what really makes us the intelligent beings we are is being able to recall and learn from experiences had over an extended period of time, also known as long-term memory, which in turn can be categorized into a few different types. Starting with semantic memory, which is our long-term store of knowledge, such as facts that you learned in school or the meaning of a slang term that's unfortunately going to stay etched in your brain forever. Then you have episodic memory, which helps us remember and recall key events and episodes in our life, like that argument you had with your partner, I don't know, 7 years ago, or the day you graduated from college. That's me, graduating from college. We also have procedural memory that helps us learn and recall how to do things. For example, typing, how to ride a bike. And finally, sensory memory, which are memories from sensory stimuli, such as a concert you attended that sounded really good, or a pizza or bread you baked during COVID that smelled and tasted amazing. So these are broadly the kind of memories that human beings have. But how do we translate these, or do these even translate into software or AI agents, which can be a combination of software and hardware applications? So if agents are truly to have the cognitive abilities we do, we need to be able to translate some of these abilities into agents. So let's see how the types of memory that I was just talking about map to agentic memory. So of course, like I said, there's short-term memory, and this typically manifests as recent conversational history in LLM applications, which includes agents. But what we are focusing on today is long-term memory in agents. And this includes semantic memory, which represents the long-term knowledge of the agent. And agents intrinsically have some semantic memory because they are trained on large amounts of information. So there is some semantic memory encoded in the weights of the LLMs. But we can also supplement the semantic memory via external databases. And these can contain any information that can help inform the behavior of the agent. For example, if you're building a customer service agent, then you could, the semantic memory could contain the information of the different applications that you offer support for. If you're building a simulation video game, this could contain information about the different entities in your simulated world. If you're building a financial trading agent, then this could contain general information about how markets work, important terminology. So you get the gist. Then there's episodic memory, which is memory of past events. And in agentic applications, this translates to sequences of actions taken by the agent to complete tasks. And here's an example of what that could look like. You could have a generalized name for the task and a description of the series of steps taken by the agent to complete it. Then you have procedural memory, which is essentially the agent's memory of how to do things. And again, there's in procedural memory encoded in the weights of the LLM. And then you have a few other things that the agent has control over. There's the agent's code itself, which defines the execution flow of the agent and constrains what actions it can take via tools. And well, correction there, agents don't quite have the agency to self-update their weights or this code, at least not yet. But what they can update is prompts or self-update. So say you have a system prompt for the agent, but during the course of its interactions with the user provides more additional useful instructions for the agent can update the existing prompt to incorporate this info. And finally, there's working memory. And this is information that the agent holds in its context window as it's working on the current task. And this can be user inputs, outcomes from tool calls, the agent's own planning and reasoning traces, and it can also pull in memories from its long-term memory store to inform its current state. And we won't worry about sensory memory for now, just because there's already enough to pack for a 30-minute talk. Plus, I think we're a little ways away from AI agents being able to process things like smells, taste, and other sensory inputs. Or I think so anyway. All right, so we've spoken a lot about the types of memory, but let's talk a little bit about how do you go about creating and persisting these memories, retrieving them in a timely and efficient manner, updating memories as new ones are created, and deleting or phasing out old memories to make room for new ones. All right, creating memories. So like I said, agents aren't yet fully self-sufficient when it comes to creating memories. But thanks to LLMs, they have some forms of memory built into them. For example, the weights of the LLM are, like we saw, a form of semantic and procedural memory. But we can also kickstart some of the agent's memories. For example, we can create an additional semantic memories for the agent by creating an external body of knowledge and giving the agent access to it via tools. We can also write detailed prompts or again, create tools that the agent can use to create memories from raw information. The way I see it, there are four main ingredients that agents can use to create memories. There's the LLM's planning and reasoning traces, where it reasons through a problem and decides what tools to call, makes observations, and things like that. Then you have the outcomes of the tool calls themselves. Then there's conversations with the end user, if the agent interfaces with actual users, or feedback from the environment that the agent is running in. And again, these reasoning traces, tool outcomes are all ingredients to create memories, but they're not memories on their own. Imagine if you were to store every single detail of every conversation or every experience you have. It's just not efficient, and to a large extent, it would be unnecessary. Similarly, with agents, you want them to extract specific insights from the information that it holds in its context window or working memory. For example, if you're building a simulation video game, then you maybe want to extract specifically certain character traits, relationships between characters, or notable events in your characters' lives, rather than every single thing that happens in your game. Or if you're building a computer use agent or browser agent, then you might want to only log successful or erroneous trajectories to inform future actions. Or say you're building a code generation agent, then you might only want to log any human expert instructions, errors while generating code, things like that. So very specific things, not dump every single thing into long-term memory. And the other thing to think about when creating memories is when to create them. And I was trying this out a few days ago for a personal assistant kind of agent, and I found that LLMs are actually pretty good. They have pretty good intuition for when to create, retrieve, and update memories on their own, but you can also help them along in this process. For example, you can prompt the agent to create memories whenever a new input is received, so you can inform every response, or you can have it create memories only when a certain condition is met. For example, I saw this, I think Mem0, they're one of the players in the memory management space, and they do this. So they monitor the context window of the LLM and only create memories when the context window is close to getting maxed out. I thought that was a pretty clever approach to do this. You can also create memories at the end of every conversation. And finally, you can also create them on a schedule, say hourly, nightly. The choice really depends on what the trade-off between adaptiveness and latency looks like for your application, because creating memories means additional steps in the process, which means additional latency. Another thing to think about when creating memories is also persisting them for use later. Because without this, the memories would reside in the context window of the LLM as temporary working memory and won't be available for future conversations. So we persist them in an external database and retrieve them into the agent's working memory as and when needed in the future. And I do think this will change in the future, where LLMs might be able to fine-tune themselves with memories, but for now, we need an external persistence mechanism. And when persisting memories, it's also important to consider how to model them in such a way that you can retrieve and update them efficiently. And again, there are several different patterns to do this, but let's touch on some common ones. So all memories have a temporal aspect to them. So you always want to store a created or last updated timestamp for each record. This helps if you want to filter by timestamp, prioritize by recency, phase out memories, things like that. And this works well for episodic memories. For memories about entities or procedural memories, such as system prompts, maybe maintaining a single source of truth that updates as new information is obtained is a good way to do it. But the challenge here is that you'll need to periodically reconcile and compact the memories to prevent unbounded growth. But again, the good news is that there's some ways to deal with this, like you can summarize periodically, things like that. Cool. We've spoken about creating and persisting memories. Let's quickly talk about retrieval. Cool. So similar to creation, this depends on the application that you're designing and when you think information from long-term memory might help improve the LLM's responses. And again, it's very possible that the LLM is smart enough to decide when this should happen, but you can also introduce some control into the process. For example, again, if it's a simulation video game, maybe you want to retrieve or do some memory processing before every action because it's a very dynamic environment. For browser or computer use agents, you can only retrieve memories during the initial planning phase so that, say the current task is buying an item on Amazon, you just get like previous trajectories and have the agent execute on that. You don't really need that much dynamic memory processing in this case. And then code generation, maybe you can decide to only pull from long-term memory only when an error is encountered, so the agent knows how to resolve that error based on its past executions. The other important thing to think about when retrieving relevant memories is like what retrieval mechanisms to use. And here we can take lessons from building search and maybe at this point RAG applications and apply the same retrieval techniques as before for this new problem of memory retrieval. And the simplest search pattern that can help with memory retrieval is exact matching, which retrieves information based on a definite set of criteria. For example, retrieving memories about entities. So let's take the example of a sim again. Say two characters are having a conversation. I can extract the semantic memory about both these characters into the agent's working memory to inform their interaction. And I can use a simple exact match to do that, as long as I can identify the names of the characters. Then you can use vector search for this problem as well. And this technique is, if you've built RAG applications or search applications, maybe you already come across this technique. So let's assume you have stored past action sequences of agents to an external database. Given a new task, you could use vector search to extract successful action sequences from similar tasks during the agent's initial planning stage and go from there. I think I'm coming up on time, but yeah, there's also things like hybrid search that you could apply here, re-ranking. Really, any search or retrieval techniques that you've come across before could be applied to this new problem of memory management as well. All right, let's briefly talk about updating memories. So as agents learn new information over time, some memories might need to get corrected or updated. And the easiest way to orchestrate this memory update operation is to combine it with the memory creation. So at whatever cadence you decide for memory creation, you would also retrieve relevant memories, update them with new information, and write them back to external storage. And here's what an example of what a memory update might look like. So say you persist your agent's system prompts as procedural memory. When the agent is first invoked, you retrieve the prompt, say it's a prompt for code generation, and during the agent's interaction with the user, if the user mentions that the agent should write doc strings for every function it generates, then the agent can use this new information to first create a memory from it, reconcile it with retrieved memories, and finally write that updated memory back to the database. And finally, that brings us to deleting memories. Now, why would you want to delete memories? Wouldn't it be awesome if agents could remember everything that they ever did or learned? I don't think so. At the end of the day, you're designing software systems. So you have some constraints to think about. So basic storage is cheap, but if you want enterprise-grade storage with redundancy, backup, and fast access, these costs are going to increase exponentially as your data scales. It's also wasteful to continue to store memories that haven't been used for a long time. And finally, more isn't better if you can find what you need and quickly. So you need some way to phase out unused memories. And the way to go about this is the way you'd handle any other data, which is by imposing data lifecycle policies So monitor usage patterns and move unused data to cheaper, slightly slower archival or cold storage at a certain cadence that you determine based on analyzing usage patterns. And regardless of usage, you would also need to impose retention periods to periodically delete the oldest and unused records. And that's really it. That's my speed run of how to think about managing long-term memories in AI agents. And I think I'm out of time, so I'm just going to leave this QR code here for you to connect with me and take a few questions if you have time for those.